Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. And today, this lecture is Lecture 18. Today we're going to discuss distribution functions. Distribution functions are covered in Lecture 19 of the text. We'll go on at some length about them and we'll illustrate some approaches to it. So what is the general motivation? Why would we want to introduce yet another set of functions? The first point is as follows. Suppose you're discussing molecules in a liquid. Molecules in a liquid are fairly closely packed. They have potential energies that actually go off toward infinity, and therefore at every moment molecules in a liquid are interacting with a substantial number of their neighbors. As a result, for starters, if we talk about gases, we talked about kinetic theory of gases, and the image was the gas atoms move in straight lines and occasionally run into something else and bounce. You cannot treat liquids like that and get a reasonable description of a real liquid. The liquid molecules all interact with their immediate neighbors perpetually. So, one thing you could though say is, well, we could calculate a partition function for a capital N atom system, couldn't we? And the answer is, well, in principle you could. However, if the interactions of large numbers of atoms are involved at once, and you do a cluster expansion, you reasonably expect that you're going to need a lot of terms in the cluster expansion in order to get something like the right result. That can't be done trivially, but it's possible to do, at least for very small systems like 5-atom systems. You do have some alternatives for evaluating partition functions. For example, there is a set of computer experiments, two sets of computer experiments known as Monte Carlo simulations and alternatively molecular dynamics. In Monte Carlo, you generate a random arrangement of the atoms and you evaluate its potential energy, and this gives you the contribution of that random arrangement to the free energy of the system. The problem with that is that if you try this with a liquid, most of the configurations refer to states of the system in which atoms are inside each other, and these states have statistical weight 0. Your alternative to this is molecular dynamics, in which you put the molecules into a box. You say they have potential energy, they have initial velocities, and we will use numerical methods to integrate Newton's laws of motion, position versus time. Now, if you actually try to do this for real molecules and you want to get results that are worth anything, you have to work very hard on making the calculation efficient. Once upon a time, I had a student who blandly listened to my description of the very large Fortran program we have to do this, and asked, well, why don't you do this on a spreadsheet? And a little discussion revealed that the notion of execution time on programs had somehow never been brought up, since a lot of people are used to programs where you press the button and it's done. The program I'm talking about, which was very heavily coded for efficiency, you press the button and you come back and check it every day for a week. You check it every day just to make sure it's executing and hasn't run into some issue. And it will take, with a modern, very high-speed machine, very long times to do. Nonetheless, one of my former undergraduates, Paul Whitford, did Lennard-Jones simulations. We did 125,000 atoms in a box, which is a much larger number of atoms than almost anyone else you can find in the literature did. And we found a number of things saying we actually used the right number of atoms, and people who used 1,000 or 2,000 atoms have some serious problems with their calculations. So you work on this and you can sort of get it to work. What the question is, what else you could do? There's another problem with saying, well, we'll integrate the canonical partition function. Suppose you could compute analytically the canonical partition function for example, argon atoms in a box for a large number of them. Q of nVt is a continuous function of v and t. It's not really a continuous function of n because you either have a particle or you don't. That's actually not quite true, and we'll get to charging processes in a later lecture. But you could certainly imagine varying the volume in a continuous manner. If you do that, anything you calculate from Q looks as though it ought to be a continuous function of V, for example, the pressure. The difficulty with this is shown in figure 19.1. And figure 19.1 gives a plot of the pressure as a function of the density of particles. Density is the inverse of volume. So we start on the left side with a large system, and we start compressing it, and the system gets smaller. Well, what happens with a reasonably realistic fluid system is you start compressing, the system gets smaller, and the gas pressure increases. The gas pressure at first might follow the ideal gas law, but after not much at all, you see the larger virial coefficients coming in, and the gas as a function of 1 over V, which is the same as density, increases as a smooth curve. And this persists until you form the liquid. And now you have a container which has gas in one part of the system and liquid in another, and you start compressing it further, and you make the interesting discovery that the Gibbs phase rule really works. You have one atomic material, you have two phases in contact with each other, and therefore you have only one free variable, the temperature. The pressure is not free, it's fixed. And so as you change the density, the pressure just sits there, and it continues to sit there until you've made the volume very small indeed, and there's nothing but liquid left in the container. And if you continue to compress the system, you discover the pressure goes up rather rapidly because liquids don't compress very well. There are 2 points, which are phase transitions, where you are crossing the line from gas plus liquid to one-phase regions. At those 2 points, for thermodynamics, the assertion is the transitions are sharp. Okay? Well, that's fine, but if you tried calculating the pressure using the canonical partition function for this system, assuming you'd somehow gotten your hands on it, you might sort of expect that G, there are only capital N terms in the, well, the largest term involves all n atoms at the same time. And therefore, if you're getting polynomials out and you're being accurate, you run out of polynomials, and therefore the pressure versus density ought to be writable, it would appear, as a smooth function of capital N. And that's shown in figure 19.2. And 19.2 shows the pressure versus density of a small finite system. And at the 2 places where there were phase transitions, the transitions should be smooth, ideally. And in between, something happens which is represented as the stair-step line, or whatever it is, which I very definitely did not claim to be putting in with any accuracy. However, the net result of this is there are transitions, and the transitions are smoothed out if the system is finite. Gee, how do we get around this? Well, if you say we want statistical mechanics to agree with thermodynamics exactly, you go into what is called the thermodynamic limit. That is, you make the system really, really big. N goes to infinity, V goes to infinity, density is a constant. And if you do that, which you can obviously do, if the limit exists, then you hope that figure 19.2 crosses over and looks exactly like figure 19.1. There is one thing you might say is you could propose that at the transition point, the virial series ceases to converge. That is, the reason you hit the sharp crossover is you can write a virial series, the series is not convergent, and when you fix what's going on, you get the sharp change. You want to think a little carefully about that, because that says you can't get continuously from the gas region into the liquid region. But you can. You just take the gas, you heat it up very high, you move across to the desired density at very high temperatures where there's only gas, or at least only one fluid. You come down again to the liquid, and everything, you haven't crossed any phase boundaries, and you've gotten from point A to point B. There is another class of systems which actually shows the behavior seen in figure 19.2. Now, what would that, how could you imagine a system that would do that thermodynamically? And the answer is you'd want a system that did not have the thermodynamic limit. For example, and I'm choosing this one not at random, suppose you had a system in which one of the phases had the physical property that its maximum volume was a constant. That is, if you tried to stick more and more atoms into the X phase, you couldn't attach more atoms to a volume with X phase because they would refuse to attach no matter what you did. You might be able to make multiple copies of the X phase if you had a really large system. However, each of the copies would have a finite volume, and therefore you couldn't do the thermodynamic limit for one of the two phases. In this case, you might get something if you'd chosen exactly the right system, like figure 19.2. Of course, some purists will say, thermodynamic purists, when they are confronted with the physical example that does this, that they have a precise meaning of the word phase, and these things that insist their maximum volume is constant, therefore cannot be viewed as phases. The contrary position is they are a phase, and the understanding of phases has to be improved a bit. Now, do we actually have things that do this? Yes, we have micelles. What is a micelle? Well, a micelle is soap molecules in a liquid. A soap molecule has one end that is highly water-soluble, and a second end that is anything but water-soluble. So here is a soap molecule, got a water-soluble end and a water-insoluble end, and at low concentrations it dissolves in water. However, if you put enough of these into solution, they start hunting around for their neighbors. They're the neighbors. And they arrange themselves, this is a little harder to do by hand, so that all of the water-insoluble ends are next to each other, and all of the water-soluble parts are out on the surface. And they form little bubbles that are water-soluble out here, and are really pretty much like gasoline or something in the middle. Of course, this means you have this thing sitting here whose middle looks like gasoline. It's happy to dissolve things such as aliphatic hydrocarbons that you cannot dissolve in water. Gasoline won't dissolve much in water. Fats won't dissolve much in water, but they're happy to go into one of the middle of one of these and sit comfortably. Or, for example, naphthalene, mothball flakes will not dissolve in water, but it'll sit happily in the middle of one of these and be dissolved and float away. However, micelles have a packing constraint. You have to have the molecules arranged so that the hydrocarbon tails are next to each other, the outsides are next to each other, and they won't cooperate and do this if you try to do too many. And if you have spheres, there's a packing limit because eventually there's only so much surface area on the outside, and they can't all fit in the middle. One response these things have is to change shape, and you get micelles that are long cylinders, and that can help the packing for some systems. But for other systems, you're stuck. You have to pack them as spheres of a certain size. And therefore, micelles, if you say this is a micellar object, if you think of it as a phase, it has an upper volume limit. And if you measure things such as the chemical activity of the amphiphile, this is an amphiphile, the one molecule. If you measure the chemical activity of the amphiphile in the system, you make the interesting discovery that the chemical activity looks very much like figure 1.7. That is, the activity goes up until you start forming micelles. Once you start forming micelles, the concentration of amphiphile not in micelles is almost constant, and you keep doing this until you fill the whole system with micelles. And if you measure the activity of the chemical activity or whatever, you get a curve that looks like figure 19.2, in which there is a transition, but the transition really is not sharp. Okay, so if you try to do this with virial expansions, though, you at least need a humongous number of terms. You have had the entertaining task of calculating B4, or at least B3. To do the same thing for B19 takes a little more work, because if you think of B19, there are 19 interacting atoms in the cluster, and there are lots of different ways to say I have 19 atoms. They are either linked or not, and the 19 linked or not atoms, there are a lot of combinations of links and no links in those 19-point graphs. And while you can throw some of them out and show that others are the same topologically, you have to do a lot of cluster integrals. That's why the last thing discussed in the last chapter is the G symbol as a replacement for the F symbol, as a replacement for combining graphs with each other. Okay, so having said that, we ask, is there another mathematical way to advance? Can we do something else instead of doing cluster integrals that might help us solve the problem? And the answer is yes, there are distribution functions. Okay, we're going to have to show you what a distribution function is. And we start off with equation 19.2, which is the distribution function for all capital N atoms in the system. It's the probability of finding the capital N atoms at a set of locations R superscript n. And it's e to the minus beta u over z. Z is the configuration integral, the total probability for all positions, combinations of positions, and e to the minus beta u is the non-normalized statistical weight for the one state. What we now do is to say, suppose we were only interested in the positions of little n of the big N atoms. What do we do to describe the position of little n of the big N atoms? Well, we can imagine introducing a rho n, superscript n, that's equation 19.3, and it's labeled as S specific because we're specifically saying that it's atoms 1, 2, 3, little n, whose positions we're interested in. We can get that function from 19.2. We get it from 19.2 by going in and integrating over the coordinates of all of the other atoms in the system. Why does that work? Because if we integrate out all of the other atoms, we are adding up all of the probabilities of what they're doing, given that we're only interested in what one or two or three atoms is doing. This is a reduced distribution function. How do you calculate the probability of die roll of one die when you actually rolled two dice? Well, you look for all combinations in which the one die came up correctly. There'll be 6 of them for a d6, because the other die could have done anything, 1, 2, 3, 4, 5, 6. And you add up over all the 1, 2, 3, 4, 5, 6. With me so far? Mm-hmm. Okay, so we've done that. That's the specific n-particle distribution function. And on the right side of the equation, you notice we're integrating out over coordinates n plus 1 to capital N. Well, that's fine, except, we've done that integration, but do we really care that it's atoms 1, 2, and 3 on the left side, or do we just want any 3 atoms on the left side? And the answer is we usually just want the generic. We'd like the probability of some atom at 1, some atom at 2, and some atom at 3. And 19.3 does not give us that because it's actually specific atoms 1, 2, 3. Buried someplace in 19.2 is, yeah, we've got 3 atoms at these 3 points, and they're atoms 4, 5, and 6. That sounds a lot more complicated, but it really isn't. The reason it's not a lot more complicated is that if you actually reach into this thing, it doesn't matter, if the atoms are all identical, it doesn't matter which atom is at 1, at 2, and at 3, my 3 fingertips. The probability is the same for all of the atoms. So we will have a whole lot of terms giving the probability that there are 3 specific atoms at these 3 points. But all of those terms are equal to each other, because it doesn't matter which atoms there are. Comfortable with that? Mm-hmm. Therefore, we just compute the value of one term and ask how many different terms, identical terms, we just found. Well, 19.3 is the value of one term. How many terms are there? Well, there could have been capital N atoms at location, any of these 3 locations. That leaves capital N minus 1 terms left for the next, and capital N minus 2 left for the 3rd point. So the answer is there are n times n minus 1 times n minus 2 for 3 particles, etc. How do we write that efficiently? We do it as seen in 19.4, namely n times n minus 1 times n minus 2 for a 3-particle system is capital N factorial, which gives you the n minus 1 and so on, over n minus little n factorial, and the denominator divides out n minus 3, n minus 4, n minus 5, and we end up with equation 19.4. And 19.4 is the generic n-particle distribution function. It's called generic because it doesn't care which particles are at locations R1, R2, R3, just that there's some particle there. So far, so good? And we seem to be doing, okay, I thought the camera was out for a second. Okay, so now we pull a trick. And the trick is to look carefully at equation 19.3 and ask what the dimensions of rho sub s, the specific n-particle distribution function, are. We can actually also look back at 19.2, which was for capital N. The numerator is an e to the minus beta u. It has dimensions 1. The denominator is an integral of e to the minus beta u over the volume for each of the n positions. So the dimensionality of capital Z is v to the capital N. Okay? What about now 19.3? Well, there's a v to the capital N in the denominator as the dimensions. And in the numerator, we integrated over coordinates little n plus 1 to capital N. And that gives us a whole bunch of factors of capital V, which cancel most of the downstairs factors of capital V. So what we can do is to say either of the rows has units v to the minus little n. Yes? What we will do is to factor those factors of v out. We can imagine doing it. How do you factor something that isn't there? Answer: if you are factoring out something that isn't there, you simply multiply by 1 in the form, in this case, v to the little n divided by v to the little n. That's 1. You leave a v to the little n behind. You take another v to the little n outside. And what happens to the v to the little n when it goes outside? Well, as long as little n isn't too big relative to big N, n factorial over n minus n factorial is very nearly n to the little n. And now we're going to divide it by v to the little n, and what's n over v equal to?
That's it.
Rho.
Yes, n over v is rho. And so, or if you prefer, since we're using rho for something else, concentration C. So as shown in 19.5, the generic distribution function is concentration to the little n power, at least very nearly, times something which I've now labeled G. And what is G? G is rho to the little n multiplied by v to the little n, and G therefore has dimensions 1. So what I did in 19.5 is to factor everything that was giving G, or rather rho, units outside, and I am left with something that's dimensionless, has dimensions unity. Check?
Mm-hmm.
Well, that G has a name. It is the radial distribution function. The radial distribution, the reason it's called radial, as though there's one radius involved, is the radial distribution function that comes into calculations a great deal is G superscript 2, the two-particle radial distribution function. And for two particles, spherical particles, G is only a function of how far the particles are apart. It doesn't care where the particles are in the system, and it doesn't care what the orientation of the particles is. So far, so good. Well, so that's G, and it's dimensionless. And that says, if it's dimensionless, we can formally write equation 19.6. And 19.6 says that little g can be written as exponential of e to the minus beta w. And w is something we just introduced. W is the potential of average force. Okay? It's a name, but it's a quite valid name. What properties does W have? Well, first of all, suppose we have two atoms in a liquid and we move them far enough apart. If we move them far enough apart, their potential energy has faded away. Fluids have ordered structure. They have a radial distribution function, which is what we're going to talk about. But the structure is only short range. We'll get to what short means in a second. But if the particles are really far apart, like this, they don't interact with each other at all. The probability of particles being here or here or here is independent of what here you choose, and therefore G must go to a constant. It must go to 1, because the probability of a particle here and a particle there, if they're really far apart, is just rho squared. So G goes to 1 at large distances, and therefore what does W do at large distances? It must also go to 1. No, it must go to 0. If G goes to 1, e to the something equals 1 means W goes to 0 at large distances. So that's the potential of average force. Okay, well, the potential of average force, I wrote it out explicitly in terms of what G is in equation 19.7, because on the left of 19.7 you see an e to the minus beta W, and on the right of equation 19.7 you see what the n-particle distribution function is, and yes, we factored that capital V out. Okay. Now, the last point I want to make, and we're going to show this in some detail, is that W is not the small n particle potential energy. That is, you might think, well, isn't the potential of average force simply the same as the n-particle potential? That looks very seductive as an argument. And the short term is that no, it's not at all. You'll see, if you'll sharpen your impression of why it isn't. And in a certain sense, the difference between people who understand statistical mechanics and the people who do not understand statistical mechanics is that the former think that W and U are quite different, and the latter think that W is U. Well, I should put in a qualification on that. If you do a pseudo-virial expansion for the two-particle distribution function, the lowest order term is e to the minus beta U. However, there are more terms, and clearly once you've added more terms in, it's not e to the minus beta U anymore. Let's try to consider why the n-particle potential of average force might not be the pair potential, or some of the pair potentials. Here are two atoms, yes? They interact with each other at these 2 points. Now, if we were to dilute gas, W would be very close to U, because the upper order terms in W would be essentially 0. However, let's run up the density. Here are the two interacting atoms. And now I bring in a third atom. Okay? And we ask, what force is the third atom putting on atom 1? Simple case 1, atom 3 does not interact with atom 2. It passes right through it, just as though atom 2 were a ghost. It's not very physical, but it's a starting point. In that case, it is equally likely for atom 3 to be here, and for it to be here inside atom 2, and ditto for all of the other positions, because as far as atom 3 is concerned, atom 2 just isn't there. Yes? In that case, on the average, while atom 3 may be pushing on atom 1, it's equally likely to be pushing this way, and the net result is the force that atom 3 pushes on atom 1 is 0. However, atoms 3 and atom 2, after all, are all identical atoms. The atoms do interact. And that says configurations of the system in which atom 3 is right on top of or inside of atom 2 are much less likely than configurations where atom 3 is symmetrically on the opposite side. Yes? So we have few positions here. We have more mirror opposite positions here. If the atoms all repel each other, the conformations on which atom 3 is pushing this atom to my right are much more likely than the conformations on which atom 3 is pushing atom 1 to my left. And therefore, because there are particle interactions, there is a net force on atom 1 due to atom 3. But if I integrate out all of the possible places that atom 3 should be, I've just integrated that variable out, I can write the force on atom 1 given that I have specified where atom 2 is. And some of that will be the direct interaction, derivative of U12 potential energy. And some of it will be the fact that because I've told you atom 2 is where I'm holding it, it must be the case that all of the other atoms are distributed to reflect this fact, and therefore all of the other atoms, on average, are pushing atom 1 this way. So there's an average force, and it's not the same as the pair potential. If only the pair potential were acting, then the force between these two atoms would be the same, no matter whether atom 3 were there or not. Well, atom 3 is there. Gotta live with that. Okay, so atom 3 is there, and it has an effect. Pardon me for a moment. But I gave atom W a name. I called it the potential of the average force. Now, I can call it anything I want. I can call it George Washington's favorite book. And that won't make it George Washington's favorite book. He's dead, for one thing. However, I can show you that W really is the potential that corresponds to this average force I just described. And we first start by asking, well, what is the force on atom 1 due to all of the other atoms in the system? And we write that in equation 19.8. And in equation 19.8, the total force on atom 1 is the sum of the forces on atom 1 due to all of the other potential energies, yes? And the force is the gradient of the potential energy. It's the gradient with respect to the position of atom 1. And if we have simple pair forces and no angular things, it's grad 1j, U1j. U1j, the potential energy between atoms 1 and j, only depends on the scalar variable R1j, the distance between 1 and j, and therefore the gradient is giving you everything. So far, so good?
Yeah.
Okay. Well, that's very nice. So there's the force. So let's take its average. And the average looks like every other statistical mechanical average you've taken in the last some months. It's seen in equation 19.9. The only difference between 19.9 and other averages is that it's gotten a little bit bigger, and I have done some front cancellations. The full average would include an average over all of the momenta of all of the atoms, and that contributes to the partition function and the statistical weight the same way, and that in the end cancels out. So only the position variables are left. Furthermore, we are interested in the average for the specific case that atoms 2 through n are fixed and unable to move. That is, atoms 2 through little n are at specific locations and are creating a force on atom 1. So we are calculating the average force on atom 1, given that we know, say, that atom 2 is over here. Everything else is free to move. We're calculating the average force on 1 when we've specified where 2 is located. And that is what you see in 19.9. And all I've really done is to take 19.8 and stick it into a reasonable definition of the statistical mechanical average. That looks a little complicated. Can we simplify it at all? Well, one thing you can do to simplify it at least for the two-particle potential of average force, is to notice I have an atom at my left fist, I have an atom at my right fist. The line between these two is cylindrically symmetric. We're equally likely to have a neighboring atom up here or down here. And because it's cylindrically symmetric around this axis, the force can only depend on F1 2 hat. That is, an atom up here will be pushing down, an atom down here will be pushing up, but all of the components of the average force on atom 1, due to the fact that atom 2 is fixed here, those forces average out and only can be lying along this line. Yeah, for any particular atom there are other force components, but they all average to 0. Well, having said they all average to 0, what can we do to take advantage of that? And that's seen in equation 19.10. And what I am saying is that if you select out this one component of F1j, the component of F1j parallel to R1 2 hat. So for each other atom is applying a force, say the atom up here, and part of that force is parallel or anti-parallel to this vector. That's the only component you have to worry about. And we can sort out that piece of the vector as done in 19.10 with an R1 2 hat, R1 2 hat. Have you seen that math trick before in some guys? It's done in quantum mechanics with projection operators. Okay, so we take this trick and we stuff it into equation 19.11. And 19.11 gives us a force which lies along the desired axis and has a whole bunch of things inside. Now we say we can do an identity on the exponential. And the identity on the exponential is the replacements in equation 19.12. That is, we're going to calculate the gradient with respect to 1 of e to the minus beta u. We're going to calculate how e to the minus beta u changes when we displace atom 1 infinitesimally. And so the gradient, which is a bunch of derivative operators, attacks the exponential. And when it attacks the exponential, it brings down a minus beta grad of u. That's the middle equality. However, we can replace minus beta gradient with respect to 1 of u with the gradient with respect to each of the terms of the potential energy. And that's done in the last piece of 19.12, where we've replaced grad 1 u with a summation over all of the atoms of not du dr1, but du dr1j. And by the way, there's a mistake in equation 19.12. The final derivative, which is a dr1, that should be a dr1j.
So it should be du1j over dr1j?
Correct.
Okay.
Yeah.
The last thing I will do with this identity is to take the minus beta that is in front of the summation sign and divide it through and get it all the way over to the other end of the equation. That's just a division by minus beta. Now, at this point we have summation j equal 1 to n, this is the right side of 19.12, and a bunch of objects. But if you look hard, that's exactly identical to most of the top right of equation 19.11. You have the summation sign, you have an r1j hat, you have a du dr, you have an e to the minus beta u, and they're the same in equations 19.11 and 19.12. The only thing that is not the same is the r1 2 hat, which is just a constant and can be moved away the distance. Okay. So having said this, we will now take and replace that whole complicated thing in 19.11 with what 1912 lets us do as the replacement, and that's seen as equation 19.13. And in equation 19.13, there are some vectors that simply pull out the right component. There's the gradient with respect to 1, which means it's what happens when we move particle 1. There's a beta inverse that's from the left side of 19.12. We divided it all the way over there. And then what is left, instead of having the du dr and other things, there's an x minus beta u. And if you look at that, I've done that replacement, and G, you see what we have there. Okay? Have I done something else? Oh yes, I've multiplied the equation by 1. I multiplied the equation by 1 in the form of capital Z over capital Z. Well, that's just 1. Unless I tell you to evaluate capital Z, that's not even really a problem. But we now have the form seen in 1913. And 1913 is the same as 1914. I've replaced that object integral dr3 drn with e to the minus beta w, because if you check back, that's what e to the minus beta w is. It's the potential of average force, and it's another way of writing the small n particle distribution function, which appears both in the numerator and the denominator of 1913. Well, by any of several steps, you can recognize that 1914 is a logarithmic derivative, and you end up with the final result, 19.15, which shows you that W superscript 2, the two-particle potential of average force, is indeed the average force on particle 1, given that I have specified where particle 2 is. I am amused to note that once upon a time, a very large number of years ago, this was a major sore point in my PhD thesis, in that there was great disagreement with bunches of people in my research group, and they were firmly convinced that W was actually U, and my claims about the potential of average force were wrong. However, in the end, well, this was not necessarily unknown before then. I regenerated what you have just heard, and that settled the question, because you couldn't argue with it. Next time, we will continue with applications of distribution functions, and we will push ahead, and I think I will talk about at least some other uses of the distribution function, such as the chemical potential. The chemical potential is significant because it introduces charging processes, an idea that can be traced back, and it actually originally appears in Josiah Willard Gibbs' original book on statistical mechanics. However, we are out of time, and therefore class is dismissed.